Hello, welcome to this clip looking into a rather applied combined spectral analysis level response question. So having a look at the question, there's quite a lot of information. We have some functional group testing information. We have a carbon-13 NMR spectrum for one of the compounds. We have some hydrogen NMR data, and we also have some information at the top about the molecular formula, and one of the compounds is alicyclic. So the best thing to do is to think about how you're going to organize the layout of your answer first. So we'll start with the functional group tests. Then we need to leave some space to talk about them. So put a subtitle talking about the carbon-13 NMR analysis for D. And then some space for the hydrogen NMR analysis for E and F. So I didn't need much space for the carbon-13 NMR, because you can see there's only one small bit of information really there. So I don't need to spend lots of time talking about that. But I need to leave a lot of space for my hydrogen NMR analysis, because there's quite a lot of information to think about. So the structures can be put anywhere. I can put my structures on the actual spectrum themselves if I need to. So starting with the functional group tests and process the information. D is oxidized by H plus and CR2072 minus. So you can see it goes from orange to green. There's no change with 2,4-DNP, so it's not a carbonyl. So that must mean it's a primary or secondary alcohol. It's not going to be a carbon-carbon double bond because there's no color change with bromine. Looking at E and F, they both have the same result. There's an orange precipitate, so it must be a carbonyl. But there's no color change with H plus and CR2072 minus. So it must be a carbonyl that can't be oxidized any further. It also has no carbon-carbon double bonds. So therefore, we're having a ketone here. And it's a ketone because an aldehyde would have also been oxidized by H plus and CR2072 minus. So you would have had a green solution here as well. So looking at the carbon-13 NMR spectrum D, just blocking out the hydrogen NMR data for a moment, and looking at the actual information, it says it's got 3 peaks. It gives you exactly where they are. One's at 24, one's at 36, and one's at 73. So we know from the molecular formula C5H10O that there's no chlorine or bromine. So it can't be this. So even though the peak positions overlap this particular environment, we don't need to worry about it because there's no chlorine or bromine present. So the next part is to have a look at the hydrogen NMR analysis for E and F. So I'm going to use the table method for this. There's no integration trace or relative peak area information, so the analysis will rely entirely on the environments that are actually present. So let's start with E first of all, and let's put the data sheet for hydrogen NMR chemical shifts. And we can do table like this. So if we label the peaks A and B, we can take their values. So their chemical shift value 1.1 is here, which is RCH for A. It's a triplet, so that means there's 2 adjacent hydrogens, so it's H2CCH3. Following the same idea with B, 2.4 parts per million, roughly here. We know it has to have an oxygen there somewhere, so it's HC to C to double bond O. It's a quartet, as you can see, and it's got 3 adjacent hydrogens as a result, applying the N+1 rule. So H2CCOCH3. I'll explain in a moment where these H3s and H2s come from. So let's do the same now for compound F. There's 3 peaks this time, A, B, and C. So following the same idea, I've highlighted in red the adjacent hydrogens, and therefore where those hydrogens might go in the possible conclusion. And the conclusion is basically the sections of the structure that I think actually might exist, based on an update of the environment from the data sheet. So taking the structures now, compounds D, E, and F are isomers with the molecular formula C5H10O. So they all have that molecular formula. And one of the compounds is alicyclic, which has got a ring structure, but it's not aromatic. So I mentioned a moment ago why I was starting to use so many hydrogens. I need to start to think about how I'm going to use up 10 hydrogens, really, because if you look here, you can see C5H10O. So that's where all these H2s and H3s, etc. came from. I need to be able to build up the number of hydrogens in my structure. So I have the freedom to do that with my molecular formula I'm provided with. So, going back to all the information we've worked out so far, D must be an alicyclic alcohol with 3 carbon environments. There's 2 possibilities. There's pentanol, or we have 2,3-dimethyl cyclopropanol. Sorry, that wasn't pentanol, it was cyclopentanol. So let's go to our compound E. So we've got a ketone there, like we said. The symmetrical structure has 2 hydrogen environments. So here's one hydrogen environment there, and the second hydrogen environment is there. The middle one isn't a hydrogen environment because it's carbon with 4 bonds already. So there's no protons here. So this is one environment. This is the second environment. So compound F gives us something like this. So the structure has 3 hydrogen environments. It's got one there, it's got one there, and it's got another one here. And this environment here supports the multiplet. So the multiplet would be because of the adjacent hydrogens, the 6 adjacent hydrogens and 2 CH3s here. Okay, hopefully it's been a useful look at this type of more applied question. As always, thanks for listening. Until next time, see you soon.